Welcome back once again. My name is Mr. Charles Wenike. In today's video tutorial, we will be discussing on dielectric loss theory. In my previous video, I have discussed some various video on based on dielectric in liquid and in so many areas. But in today's video is a different video altogether, but it will also help you if you have watched my previous video based on on the topic of dielectric, this one will also be a help for you to understand better and more about dielectric. But before we proceed on today's video, I would like to say, please, if you like my video, subscribe to my channel, comment, like, and share. Thank you once again for watching. My name is Mr. Charles Wenike. So in today's video, we'll be discussing two important factors of dielectric theory. The number one is imaginary dielectric theory, and the second one is the real dielectric theory. So those are the two things that we'll be discussing in today's video. So let's proceed on that. So in that case, the permittivity of dielectric material has both real and imaginary mathematical representation. It has both imaginary and real mathematical representation. In this video, I will not give you or write out any formula as the case may be, because it might involve formula, but formula might or will not be involved because I am not going to make it or add any formula to it. But the fact is that I'm going to explain it very well for you to understand. So the real is different and the imaginary is different, and they are represented in front of in terms of mathematical presentation form. So in that case, this imaginary part of permittivity describes the energy loss from an alternating current signal AC. The short form is AC, as it passes through the dielectric. I repeat, the imaginary part of permittivity describes the energy loss from alternating signal, that is from alternating current signal, as it passes through the dielectric. It simply means that on the process in which when the current is passing through the dielectric, this imaginary signal is one that is telling you the losses of the dielectric in it. So in that case, the real part of the permittivity is also called the electric constant or relative permittivity. You can call it electric constant. You can also call it relative permittivity. So that is the real part of this that I'm explaining. Just as I said, from the imaginary is the one that dictates or gives you the information of that. In fact, it uses the AC aspect of it. Imaginary uses the AC, while this particular one, being the real, is talking of, you can also, it swapped the name, which it could be called electric constant or relative permittivity. So the permittivity of a material describes the relationship between an AC signal transmission speed and the dielectric material capacitance. What do you understand by that? What I'm trying to explain here is the permittivity of a material describes the relationship. It describes the relationship between the imaginary and the material capacitance. The material capacitance, it simply means the volume, the capacity in which it can carry. So it means that the relative or the permittivity is just there for him to relate the capacitance of the dielectric material and the imaginary aspect of it. And remember, imaginary aspect of it, it has to deal with AC signal. And I told you that in my previous video, which I discussed of DC and AC, AC is a pure electrical current, while DC has been converted from AC to DC. So imaginary, it has to deal with AC. It has to deal with pure electrical current. So the permittivity is the one that describes the relationship between an AC transmission speed and the dielectric material capacitance, being the volume in which it can carry. So in that case, when the word relative is used in front of permittivity, when the word relative is used in front of permittivity, the implication is that the number is reported is reported related to the dielectric properties of a vacuum. I repeat once again, when the word relative is used in front of permittivity, the implication is that the number is reported relative to the dielectric properties of a vacuum. And we all know what vacuums is all about as a physics student or electricity or as an electronic student or electrical student, we all know what vacuum is all about. So I don't need to explain much about vacuum. So in that case, the imaginary part of the dielectric permittivity, which is a measure of how much field is lost. Remember what I said before, the imaginary part of the dielectric permittivity, which is measure of how much field is lost as heat during polarization of material by an applied alternating electric field is also termed as dielectric loss. Remember what I said. Most importantly, what I want you to understand between the imaginary of permittivity relative distance is the difference between the imaginary and and the real is this. The imaginary part of that electric, which is measure how much field is lost as heat during the polarization of a material by an applied alternating electric field is also termed as dielectric loss. That imaginary which it measures during in times of alternating being AC field, it is also called or it can be termed as dielectric loss. The difference is it uses AC alternating current signal, while the other one it is it is different from it. How is it different? It's different because the permittivity, which can be called the constant, called dielectric constant and relative, they are different. And in front of it is described the relationship between the so-called permittivity and between the imaginary and the AC signal, how it works. So I want you to think of something that is real and something that you are imagining. The real is what we see, the truth. Let me put it in that one. Why the imaginary, it could be truth. It might or it may be false. And imaginary is in between probability. Let me put it in that form. So why the real is things that we see. Yes, this is the result of 1 plus 1 is equals to 2. I know why I'm trying to make it easier for you and I, because some of you might be thinking, what is it saying? So it's just for you to understand it in a way that you can be able to write it down in case if you are asked to put it in black and white. So let's proceed more. The characteristic orientation of the dipoles, because there are something that I would like to use. There is a diagram which I would like to use to explain some certain things that I'm about to say now. So in that case, the characteristic orientation of the dipoles in an electric field result in a frequency variation, dielectric constant, and loss over a broad band of frequency. some of you that maybe as you are hearing my voice, you'll be saying, what is it saying? I don't really get that. Maybe, I don't know if you are new in terms of dielectric, this course of dielectric, you should go on my videos where I have already made some videos on based on dielectric losses. You understand some basic form or aspect of it because I have already treated this video, this particular topic severally, and this one is the addition of some certain things which I have not treated, which I have to add in the theoretical aspect of it, which I differentiate the real and the imaginary. And this one that I'm trying to explain here is the characteristic orientation of the dipoles in an electric field result in a frequency variation. Whatever thing that involve frequency, it involves the variation. You know, frequency, it could be high, it could be low. It's not always constant. So as long as the variation is there, it's not always constant. And in that aspect of dielectric constant, which means the real of that electric constant has been replaced, it has been replaced by dielectric constant. Instead of using real, it has been replaced by dielectric constant. Remember what I said before about it, the real can be also be called dielectric constant or relative permittivity. But in this case, I am using dielectric constant in replacement of real. So it means that the dielectric constant represents or replace the real. So in that case, the characteristic orientation of the dipoles in electric field result in frequency variation of dielectric constant and loss. Remember, loss there also represent the imaginary. Loss there also represent the imaginary over a broad band of frequencies. So the typical behavior of real and imaginary part of this permittivity as a function of frequency is different. You know, their behavior, the typical behavior in between the real and the imaginary, they are different. They can never be the same because something that is real is real, while the one that is imaginary, which can be you can use a, let's say, a material or a microscope to confirm what exactly, if it is working the way we think or if it is not working. But from my own understanding, its work is real. That particular imaginary is real because on the process of a current passing through a cable, definitely it creates a field, and which we all know, we all use electricity in our home. So in that case, the relative permittivity of a material is related to a variety of physical phenomena. The relative permittivity of material is related to a variety of physical phenomena that contribute to the polarization of that electric material. If you understand, sometimes I use I use relative permittivity, and I also used um, dielectric constant. They all substitute or represent or replaced real in that area. Instead of me to use real, I now use um, either relative permittivity or dielectric constant. So that is how it is. So in that case, which I have already said before, the relative permittivity of a material is related to a variety of physical phenomena. You know, whatever thing that have to deal with the relative, it have to deal with the physical phenomena. That is how it works. That contribute to the polarization of that electric material. I have discussed on polarization as well. Maybe as time goes on, I will also make a video on polarization too. So in that case, the variation of permittivity in the microwave, where I will use a diagram of microwave to explain it a little bit. The variation of a permittivity in the microwave range is mainly caused by dipole realization. I have discussed all this. That's why I say watch on my previous video on my on dielectric losses. And the absorption peak in the infrared region and above are mainly due to atomic and electronic polarization or electronic polarization as the case may be. So in that case, we will be looking at some certain things. I know some of you might be saying what is it saying in this what I just said now is just a variation of permittivity, the microwave range. Well, I am going to use a microwave range. There are something that I have already tried out just to explain the cause by the dipole realization and the absorption peak in the infrared region and above are mainly atomic and electronic polarization. So that is what we are about to discuss now. Now, this is what I'm trying to explain here. Now, from the diagram above, you can see that we have dipole and related realization phenomenon. That is, I'm using this. This is let's use this as a microwave millimeter infrared visible ultraviolet waves. So in that case, you can also see the frequency. You can also see the atomic and the electronic. You can also see the draft, how it is. It started from 0 range to 10 raised to power 3, 10 raised to power 6, 9, and so on and so forth. So these are just what I was just trying to explain. And I have some other things how I'm going to also explain it much better in details. So these are the diagram. I am using this as a microwave millimeter. Maybe I wasn't able to bring maybe to substitute the microwave, but we all, some of us also have had or seen microwave in our various places or home. Even if we don't have it in our home, we have heard about it, and we all know as a physicist or an electronics or an electrical student, we know what microwave is all about. Then that is what you should just look for where microwave is and check that it has a various ranges on that frequency where you can hide it or reduce it based on what you want to make use of it for. So that is just the diagram aspect of it. So in that case, the dielectric properties of solid at microwave and radio frequency are they are highly influenced by the ionic positions and changes caused by the lactic vibration. Just as I said, in that microwave, I don't know if you can be able to see microwave within you. You can also imagine once it has been plugged on that electric. Maybe you vary it from 0 to 5 to from 5 to 10 and so on. It's depending on how you want to make it. That is the frequency variation. So what I'm trying to explain here is the dielectric properties of the solid at microwave and radio frequencies are highly influenced. They are highly influenced by the ionic positions and changes caused by the lactic vibration. Once you on it, and you put it, let's say, from the range of 5, as the case may be, there is some influence of that ionic position that has been injected on that microwave. So it will cause a lactic vibration. You will see that that thing will be on once you have once you have you have switched it on and you on it and you put it on the frequency 5, 10, 15, as the case may be, it will just arouse the so-called micro wave and the temperature. So two types of dielectric losses are identical in crystalline solid at high frequencies. There are two types of dielectric losses are identified in crystalline solid at high frequencies, namely intrinsic losses and extrinsic losses. I know some of you have all heard about this intrinsic and the extrinsic. They are all losses in terms of that microwave. During that processes, there are two types of losses in terms of the frequencies as you have varied it, as the case may be, from 5 to 10 or from 10 to 20 I don't know their personal choice. So I'm just trying to use microwave as an example to explain it to your own understanding. So in that case, what I'm trying to explain here, there are two types of losses, highly in frequency, mainly intrinsic losses and extrinsic losses. So if you don't know what intrinsic and extrinsic losses is all about, I believe that as a physics student or an electronics or electrical student, you should know that they are all um, um, semiconductors material in which we use in manufacturing of our so-called electronics, how do I put it, electronics materials, depending on what you want to make use of it for. So the dielectric dispersion in solid depend on the factor such as ionic mixes. That is the way the dielectric dispense, as in the dispersion in in solid depend on the factor such as ionic mixes. So for it to give out, it depends on that factors being ionic mixes. So that is how it works. So electric charges slash valence state of the ion, spring constant of the bond, lattice imperfection, etc. So that is how it is. So in terms of that, what I'm trying to explain here is this: the dielectric dis- dispersion in solid depend on factors such as ionic mixes and electric charge slash violent state of the ion, spring constant at the bond, lattice perfections, and so on and so forth. So that is how it is in terms of that. So the dielectric losses are close, the dielectric losses close to the lattice vibration frequencies are generally estimated in terms of in terms of harmonicity of lattice vibration. Harmonicity simply means something that is in harmony. Something that is in harmony. That is just an explanation of the harmonicity. So the dielectric losses are close to the lattice vibration frequency are generally estimated in terms of the harmonicity of lattice vibration. And I believe when I was in school as well, I will talk about lattice vibration in terms of solid state. It was in solid state physics, yes, and I can also explain much more about that. But this lattice vibration is different altogether. But as a student of electronics or physics, or as the case may be, I believe you have heard about lattice when you are passing through your university education. It's not everything so far that I will explain, and the video will be very long and you'll be tired of watching or hearing my voice. So in that case, the low frequency phenomena are responsible for the intrinsic dielectric loss in solid dielectric. You know, we are to talk about how it is now. We are to talk about this one is the low phenomenon or um, the low frequency phenons are responsible for the intrinsic dielectric losses in solid dielectric. So in terms of low, it have to involve intrinsic, not extrinsic. So the intrinsic loss mechanism occur due to the interaction between the phenoms and the microwave field, or due to the realization of the phenon distribution function. So that is, I just want you to get this thing on their memory and understand how it works, because those are the two losses on that process, the extrinsic losses and the intrinsic losses. It's very important for you to understand it. So in that case, the lactic phenom mode will determine intrinsic limit of the high frequency dielectric losses in crystalline solid. That is where to say that in that case, the extrinsic losses are occur due to the interaction between the charge defect, and the microwave field. So I want you to understand something here. I want you to understand something here, something that is very important. In terms of to differentiate the losses between the intrinsic and extrinsic. Now, the dielectric losses to the lattice vibration frequencies are estimated in terms of what the harmonicity. So here is talking about the low frequency in terms of what intrinsic dielectric losses in solid. It went ahead to discuss on the dielectric and on the intrinsic losses mechanism occur due to the interaction between the phenoms and the microwave field. Is between the phenoms and the microwave field due to the realization of the phenom distribution function. Now, in that case, when you come straight back to the extrinsic aspect, the extrinsic losses are occurred due to the interaction between the charged defect and the microwave. So these are the things that you should be able to understand how why the charges or why the losses occur on and during the process. And I believe that this is where we'll end this today's video. Please, if you like my video tutorial, subscribe to my channel, comment, like, and share. If what you said or if what I said you like it or you don't like it, maybe you can also comment below where whatever thing you want me to, any video you want me to make as well. Comment below. I believe that we can make it if it is possible. Thank you once again for watching my video. Please, if you like my video, subscribe to my channel, comment, like, and share. Thank you once again for watching. See you next week.